All right, welcome everybody. My name is Katya Wald. I'm the Executive Director at the MIT Enterprise Forum of Cambridge. Thank you all for attending today's webinar. Just so you know, I like to fair warning. This is the first time we've used the Zoom webinar feature, so we're still learning some things. But if you didn't see the slideshow, please type your questions in chat. We'll make sure to get to as many people as we possibly can with Q&A. If we don't get to your questions, you'll have the opportunity to chit chat with folks who are on today and other attendees actually in our Slack channel, and we'll share that as well. We have a really great panel, so I'm not going to do my whole spiel about the Enterprise Forum. If you'd like to learn a little bit more about us, please visit our website at mitforumcambridge.org. With that, I really want to turn it over to Andrew Maker from the Canadian Consulate. They've really been a great partner of ours for a long time. We appreciate them bringing us such a wonderful panel, and I will turn it over to Andrew.
Great, thanks, Katya. On behalf of the Consulate General of Canada in Boston, I'm excited to welcome you to today's program. We have a great panel that I think you'll agree, highlights some of Canada's best and brightest minds when it comes to quantum technologies. Canada has been a pioneer in this space, and through federal, provincial, and local programs, we've helped move quantum strategy to the forefront. While today's program will highlight on quantum technology, I encourage you to reach out to myself and my colleagues at the Consulate to learn more about how to connect with Canada across all industries, from life sciences to food to ocean technologies. We're here in Boston, and we're happy to chat with you and learn more about what your organization is doing and how we can work together. So without any more delay, I'd like to introduce Heidi Legg, moderator of today's program. Heidi's a proud Canadian-American citizen and partners with other local organizations like Canadian Entrepreneurs in New England. Heidi's founder of the Editorial, where she writes about emerging ideas across a number of stimulating and intriguing topics. Heidi's a contributor to WBUR and has been published in The Atlantic, the Boston Globe, and the Ottawa Citizen. Heidi spent a number of years at Harvard's Kennedy School, at the Shorenstein Center on Media, Politics, and Public Policy, where she authored papers on the fight against disinformation in the United States, emerging models in local news, and preserving thought leadership magazines in America, and how brand trust intersects with subscription. I encourage you to give Heidi a follow on Twitter at Heidi Legg, that's with 2 G's, to stay up to date on her latest work. So Heidi, I will turn it over to you. Heidi, I think you're on mute.
For those papers, I'm really proud of them. And as many scientists know, papers take a long time. Mine were discussion papers, not even peer reviewed. So today we have a lot of people who are deeply embedded in science, and the work that goes into research and papers is laborious, and it takes a lot of time and expertise. So I'm grateful to have a chance to bring science to the forefront these days. And we have an amazing panel that you put together. So without ado, I will move over to those joining us. I think we have some of Canada's foremost experts on quantum technology from industry and research. They've been trying to get me up to speed quickly as a liberal arts mind. I want to start by introducing Rafal Janik, head of product at Xanadu. What I love about Rafal is he told me he was a reformed academic, started his own company after working for large enterprises, and joined Xanadu, this hot new startup heading up the product side, basically everything that is not research. But he knows this subject deeply. We're also joined by Catherine Lefebvre. She has a PhD science liaison, so Dr. Catherine Lefebvre, Science Liaison Officer for the Canadian government. Catherine has been instrumental in helping me get smart on quantum, and she has a background in quantum physics and advises the Canadian government in presenting their lead in quantum. She brings a great perspective on what is going on in Boston and in Canada in quantum. And Alex Condello is Manager of Applications Development and Tools at D-Wave Systems, another hot startup in quantum in Canada. He's an American who has lived in Canada for over a decade, so we passed at the border. He comes from no quantum background, rather has a mathematical background, which certainly helps, and initially joined Devoid to take on customer service, and now he leads applications and tools teams. So that shows you that you can transfer over from the customer side to the development side. He writes open source code, he helps with production scale, and claims to know just enough about quantum physics to get himself in trouble. So I'd like to join our three guests, and I'm really excited to have the time with all of you. One thing I've learned in my time in media and studying journalism and disinformation and the future of digital news is that data is the lifeblood of the digital economy. And it has also become a political football, opposing sides dueling over who should have access to digital information that will likely determine who wins global technology, like artificial intelligence, next generation mobile networks, and quantum computing. So I want to ask you, how can quantum computers and quantum physics play a major role in this new data economy? And I'll start with you, Rafal.
Yeah, I think that people often jump onto big data as a natural, problem to tackle for quantum computing. But in fact, at least in the near term or midterm, it's not necessarily the best application. Though there is huge computational power even behind near-term devices, they're really focused on problems not that have large amounts of data that describe them, but that are rather described by a very small subset of data, but have a large number of possibilities that you want to explore. One example I often like to give is like the backpack example. Let's say you have 50 stocks you want to pick, and you want to pick the most highly correlated ones for a portfolio. In order to look at all the possible combinations of stocks that you would take up more than the computational power of like the entire Earth for many years. But for a quantum device, this is potentially a problem that they could solve very quickly, or at least provide some guesses that are very close to the probable solution. And this is a problem that's defined by only 50 data points, but the kind of probabilistic space that they would have to explore is incredibly large. So I'd say big data and the data-driven world is definitely something that people like to think and link to quantum computing. But still for a long while, really the substance of problems that we'll be focusing on are ones that have this large combinatorial space.
And Catherine, you've has the deep knowledge in how quantum is used for chemistry, quantum chemistry. Where do you see these early applications of quantum going, and what you're developing in Canada in quantum?
Yeah, indeed, quantum chemistry is probably one of the first application where we'll see, because it can also work with the noisy gates that we currently have. So like AI and dealing with machine learning and big data would need error correction on our current technology, and which we don't have yet. But quantum chemistry is probably something that we can we're already starting looking at, and we have algorithms that are running with a hybrid system of quantum and classical computers, or just with the current status of the quantum computers. So applications are certainly in drug discoveries. So for pharmaceuticals, we can design new molecules and also in materials. So the challenge actually in chemistry is to accurately describe a system, so it's atoms and electrons. So like when I was doing my PhD and postdocs, I was studying very simple molecule, H3 plus, H3 double plus. And so
this is in Sherbrooke.
When I was in Sherbrooke, and also when I continued as a research associate at INRS, Institut National de Recherche Scientifique, but definitely in Sherbrooke, I was using supercomputers, a high, like 1,000 of CPUs to model the dynamics, so the motion in time and space of 3 protons and 2 electrons. And this was taking forever. And but still we could solve that accurately, numerically. So now if you think of caffeine, or studying chemical reaction in time and space, not just finding the lowest energy state of a system, but like how it evolves in time, how we can follow the motion of electrons, how can we control those chemical reactions. It needs a lot of, we're handling a lot of degrees of freedom, so many particles at the same time, quantum particles. So it's impossible to do that with classical computers. And if we try to do that, then we have answers that are not satisfying. There's like approximation or two proofs. So this is something that definitely, this is one of the first application that is that we should see, and we already have algorithms that are running to find the lowest state. We call it the ground state of some big molecules, and then like in Canada and also around here in Boston, there are specialists in this domain.
So in quantum chemistry, can you use that to apply to geology, whether it's sort of oil and gas, or to battery? I know people are looking for a next gen battery. Is that quantum chemistry? I mean, I remember I did an interview with Keith Flaherty around genome therapy, and melanoma was the cancer that was able to be the most sort of manipulated by this new technology. What falls under quantum chemistry?
So I wouldn't call it quantum chemistry. So quantum technology is very wide, right? So the first thing that we are discussing today is quantum computing, but it has also, and an application of quantum computing for chemistry, but there's also quantum sensing and imaging and quantum communication. So if we're looking at mining application or health application, I think it would fall into the sensing and imaging. So that, and then these are like, you can use quantum technology, quantum phenomenon to study and to study like the gravitational field or the electromagnetic field, and then it gives you a measure of physical system that can be applied for oil and gas or for mining, finding new minerals, finding defects, and that are indicative of something useful for a specific business. So I would separate those.
What I found fascinating was just how ubiquitous the application of quantum technology will be. And Alex, maybe you could tell us where D-Wave is focusing their application, because you're now in the development of tools and applications. What are you focusing on at D-Wave? Which industries and areas are you looking at?
Yeah, I mean, so broadly speaking, quantum computing hopefully will have impact in a large variety of different arenas, but sort of picking up where kind of Rafal was mentioning, you know, it wants to solve a very particular type of problem, which is sort of a relatively small, hard problem. And so the trick is, can you take a large industry scale problem of, you know, many, many, many thousands of variables that might take, you know, weeks to run, and extract some hard core, some hard nugget from that problem that can be then solved on the quantum computer. And that's where sort of.
And this is because I just for those of us that are total Luddites in this space, Luddites in the space. So that's because current computer technology still has certain problems it can't solve. They're just, you're not cracking them, and you need a next gen.
Yeah, I mean, I think the way that I like to think about it is that classical computers, so our current computer technology, are very good at doing very simple tasks extremely fast. And so if you have a very, very large, say you have a phone book, and you want to find a person in that phone book, you can simply go through it name by name until you find it. And a classical computer is quite quick at that task. Now, a quantum computer, though, is very good at solving these complicated tasks where it's a small, dense problem, but have, as Rafal mentioned, a very large number of solutions. And those are sort of, they're called NP hard problems for those who are familiar with this space. Those are the kinds of problems that are easy to state, but would take, you know, all the computers on Earth 10 times the heat depth of the universe to solve. And those are ultimately the problems that quantum computing is attempting to approach and is trying to solve in the long run. And so when we look to applications, the first thing that we'd like to find is like, well, do you have one of these problems naturally out of the box, ready to go? And that's why I think, I would agree with Catherine that quantum chemistry is an early application, because those are these sort of hard problems that sort of start off in this difficult state. But D-Wave is also aware that, the optimization space, specifically industrial optimization, is an enormous space that is full of this very difficult, very large problems. And so for us, we're investing very heavily in taking these large industrial scale problems and then solving them using both classical and quantum technologies together. Because frankly, there is no future where quantum computing replaces classical computing. I mean, these are always going to be, partners in solving problems. And just like even in classical computing, we've seen the rise of sort of GPUs, this different type of processor in addition to CPUs. I imagine that the future for quantum and classical will have a large variety of different infrastructures of CPUs and GPUs and maybe tensor processing units, quantum computers, maybe different types of quantum computers, photonics, gate model, quantum annealing. All of these different systems will work together to each take a bite out of this large computing pie that we all want to solve, or this large space of problems.
And at D-Wave, what are you looking at?
So D-Wave specifically, we solve a slightly different problem than sort of our gate model counterparts, where you can basically think of it as an optimization function, where you can specify sort of a cost over a set of variables, and our system in some sense attempts to minimize that cost. So specifically, we're interested in industrial applications. That's things like protein folding, logistics problems, nurse scheduling, the knapsack problem that was mentioned before, things like if I have a set of pipelines and I want to be able to monitor those pipes from a set of junctions as cheaply as possible, how would I solve that problem? Or I have a set of antennas that interfere with each other when they're all on. So how do I create a pattern of my antennas so that I'm covering a wide area without creating interference amongst them? Or perhaps how do I route a set of robots through a warehouse in such a way that they can retrieve their packages as efficiently as possible? Those are the kinds of problems that I think quantum computing can start to affect even now. I mean, we're starting to look at that with our hybrid technologies, that we're able to provide value to different industrial partners using quantum technologies.
And Rafal, tell us a little bit more what Xanadu is trying to solve. Which space are you sort of targeting?
Yeah, I mean, we're a little bit different. We're part of the crowd that's the gate-based crowd working towards universal quantum computing. So in the long run, the machines that we're hoping to build will be very ubiquitous, as was already mentioned. There basically wouldn't be a device in the vision that we have that wouldn't have a quantum coprocessor, just because of the end game algorithms that we already know of have the possibility to impact a large number of existing classical applications. In the short term, the devices that we have online right now available through our cloud really do fall into the same realm that Alex and Catherine already mentioned. So on the quantum chemistry side, we're a little bit different. We like to look at things like vibronic spectra, which are interesting for the design of things like OLEDs for lighting and TV manufacturing. Mm-hmm. On the finance side, there's a series of problems around arbitrage, portfolio optimization. But what all these problems have in common, which was already mentioned, is that they have a small number of parameters that define them, but are computationally very difficult to find the answer. And a lot of these problems have been lost in industry. Originally, when we engaged with some partners in the—
He's nodding.
Yeah, because it's hard. We had a project with Scotia and BMO where they wrapped up a very nice project they wanted to do. And it was interesting. There was a publication out of it. It's a project that often gets mentioned around finance, which is the pricing of derivative products, which is computationally intensive, but it's more of a later stage quantum problem. But through being able to do that project, we actually managed to transfer enough knowledge to the teams within the banks that the next series of problems they came up with were much more applicable. They got the kind of caveats of what near-term quantum computing can offer. Where are the actual speed-ups? Where is the advantage? And the next set of problems they came back to us with were like right exactly in the sweet spot with what we like. You know, there's 50 parameters that can define them, but you would never even think about trying to solve these problems today because classical computers can't even begin to tackle it. So I think there's a big challenge for all the quantum companies to do a certain amount of education for potential
I
clients.
said to you guys said to you guys, it reminds me of the 90s. My husband, who's also Canadian American, we went out to California, to San Francisco, for this thing called the internet. And in a similar role to today, I ended up being the person trying to be the sort of translator between the computer people and the rest of the world. And it really was a front line of just education to have this, what basically has become the backbone of the economy in America in many ways. And do you feel like you guys are that? Do you feel like you're preaching this next wave that, so the next big boom? Because the internet in the 90s, even though it started as early as the 70s, the 90s was the start of the boom. Do you feel like you're on the front line?
It's there. D-Wave has been there since the mid-90s, so we appreciate all the work that they've done. But the real challenge is, I think the estimate is there's about 3,000 people in the world right now that truly understand quantum computing. So we need to get that number up to, 3 million.
I did find a good article on Wired, Catherine. People should go look at it. It was summer 2018, and it was quite good in Wired. It helped me along with some other documents Catherine sent me. But it's hard if you're not in the space. And so one of the things a lot of us hear about sort of, if you're just catching a little bit of quantum, and I know many people on this call are much deeper into the knowledge base, so I'll try and get to more deeper questions. But on a sort of surface level, Peter Shor invented that quantum algorithm that cracked the difficult part of factoring. And it was first published in 1984. There was sort of this freak out because everybody was like, oh my goodness, banks, national security, everything's going to be cracked. They're going to be able to crack these codes, and all of your national secrets are going to be available to the world. Where is that today, and how are you feeling about security, both for banks and for national security? Anybody go ahead, whichever one of you wants to jump in.
I'll start off because I think, security is something I'm personally passionate about. The hardware that's required for this type of, let's say attack is actually still quite far away. To give you an idea, you need about 2 times the number of logical fault tolerant qubits that they're the key sizes in order to be able to attack this. So let's say you need about 5,000 logical qubits.
Mm-hmm.
The problem is that for one logical qubit, you need about 100,000 physical qubits. And we're up to now, tens of millions of qubits needed to launch this attack. Right now, we're sitting between 40 to 60.
Yeah, I saw that. The chips that are available, am I getting that right? The chips that IBM and other
that's right.
Now are like 70?
Yeah, but it took us, 20 years to get from 1 to 5 qubits. It's not going to take us another 20 years to get from 5 to 50 million. And we're already seeing the acceleration happening quite quickly. The other thing is that this only attacks a very specific type of encryption. So this is public key RSA-based encryption, which is based on a scheme of elliptical curves. We already know other encryption schemes which are completely safe to quantum, and it's a matter of changing them over. But we're still using these old encryption schemes, and we know that there's good actors and bad actors out there collecting all our data. So all the data we're transmitting today with your bank, that the banks are transmitting between each other, when this quantum computer appears, will be decoded. So if you're an enterprise and you're comfortable in 20 years, all your data that you've transmitted being completely decoded, then you have nothing to worry about. If that represents a risk for you, which I think for most financial institutions, it absolutely does, then you should think about changing your current encryption schemes to things that we know are quantum safe. The problem with the quantum safe encryption schemes is instead of taking, a fraction of a millisecond in order to generate the key, it takes seconds to do so. So the next time you'd log into your, online banking account, you'd end up waiting 10 seconds in order to log in instead of getting in instantly, which is why the large financial institutions haven't made the jump.
So who's working on that? Tell me some of the startups that are working at making that go down to a nanosecond from 10 seconds.
So there's quite a bit, but I'd actually say that the RSA itself, which is an international body, is focused on developing the next gen quantum safe encryption. Not to get too political, if you're passionate about encryption, then world governments, the US being included in this, are actively trying to put backdoors into encryption schemes, which are much bigger risks to security than quantum will be.
Can you explain that to me?
Yeah, I mean, again, I think we're diverting a little bit too much, but they're trying to have a way to be able to decrypt communications for lawful intercepts. But we've seen that lawful intercept technology be used repeatedly for unlawful purposes by bad actors. So you can make encryption very unsafe by putting in a backdoor. And this is a fight the US did have in the 80s and the 90s already once, and it seems to be resurfacing again. So quantum safe encryption is available. People are trying to make it faster. There's startups, there's public bodies, but it's something we need to worry about, but it's definitely not the end of the world when quantum computing gets here.
I have a theoretical question that's come in, which is what about quantum computing for approaching one of the big problems in the field of information economics, the economic calculation problem?
Maybe I'll let somebody else jump in.
The choice or balance between organizing an economy with free markets versus central planning posed by Friedrich Hayek.
I mean, I'm not especially familiar with that problem, so yeah, I'll also perhaps defer.
Catherine, are you, or we can keep moving?
Yeah, I think we can keep moving, but I would like just to comment on the previous question that you put on the how worried should we be about this encryption that is not quantum safe. And just it may be very naive comment, but to me, science is about discovery, and then technology is there to improve our lives and safety. So there is a responsibility also from all the scientists and the technologists, the practitioners, to educate how to use safely the technology that we're developing, and also the responsibility of the governments to bring standards on how to use the scientific discovery for the best, right? And
that's such a huge problem when we look at the governments, that they don't, many of the governments don't have the knowledge base to do that. We look at social media, you know, Twitter today is trying to decide if they kick Trump off a platform. There's no regulation because this stuff is moving so fast. And so one of the things I found hopeful was when you were telling me that there's a national quantum initiative being created in Canada. There's an equivalent in the US that was passed in 2019 and one in Europe. I mean, these are the people that understand this stuff and should be thinking about regulation and how it's used safely. How do you see these three organizations working together, and what is Canada doing with this national quantum initiative they want to create?
Yeah, so it's actually the quantum initiative, like they coined it for that's in the US, a quantum strategy, the national strategy in quantum in Canada. So Canada is, to my knowledge, a little behind. The US has been developing its strategy, and so EU has been very active and have a very strong strategy. They call it the quantum flagship, the UK and Germany, and also Netherlands. They're all published their strategy. China is there, Australia and Japan. We're all building different national strategy. And this one, like, if I can summarize, I think that they all share this same three important points: is training. So training the quantum workforce, so people who are gonna be literate in quantum and also gonna share this knowledge with the rest of the population. Foster collaboration between research and industry so that we can commercialize technology, quantum technologies, and also in the standards. So standardize products and quantum technology so that we do it for the best of our society, and in cooperation with different disciplines and different nations.
That's always the dance, right? As we've learned from the tech boom, is that there's the dance of having no regulation, a free market economy, so that startups like D-Wave and Xanadu can thrive and move forward and take us all with them. And then also, whether it's CRISPR and genome, or whether it's quantum computing, or whether it's the internet, no regulation just kind of leaves everybody with a lot of nefarious characters that can bust in. And so I know that Creative Destruction Lab in Toronto, Xanadu and D-Wave both participated in that. Did you feel, maybe we'll start with you, Alex, and then Rafal, that the Creative Destruction Lab in Toronto had this sort of ethics core to it, or was it all just about like getting a product fast to market and getting the research ahead of everybody else?
I mean, I would say yes, and I know that there was sort of an ethics component to the overall program. I mean, fundamentally, the Creative Destruction Lab is a nonprofit based out of Toronto that is focused on keeping Canada ahead in the quantum product space. So, I mean, they're very focused on making sure that these different customers, or these different companies rather, have a sort of product. They have a project, or they're going to be large employers, or sort of good neighbors in the Canadian economy, and that's a big part of the overall focus. And I think that honestly does keep it relatively honest. I mean, that is using the sort of mechanisms of the market appropriately, in the sense that if you're focused on building a product that employs a large number of people, that's a good participator in the overall quantum ecosystem, then that allows you to stay honest, essentially. It's not these small groups of people who are potentially bad players.
How many people were in this CDL, the Creative Destruction Lab, when you were there?
I mean, so each cohort, I think, has about 50 to 100 people, something like that. I think on average, they tend to come out with, it's a tech incubator, so there's sort of a narrowing process, but we're currently continue to be engaged with maybe 5 or 10 companies that came out of them. And then I know that there's a large number of other companies that, ended up working on different quantum or quantum inspired products. So, it's churning out a decent number of startups in this area, and some of them have been quite successful. And Xanadu, I mean, is one of the most successful to come out of the CDL, obviously, and has sort of joined the field in a really great way, because, maybe this is a question that will come up later, but like the field right now, because it's so open, is still very, very friendly. And like, we're still very excited to have more people come into the field, because right now, as touching on a previous question, there's still so much education to be done. And there's still so much just sort of building an ecosystem and getting enough people that you can really get sort of sparks flying and ideas being thrown around and ecosystems being built. And so, we're still at a point that we're just excited to see more technologies coming in, and it's such a wide open space that it's not very threatening yet.
Because Silicon Valley, that was sort of the magic that happened there when it was small. And then Kendall Square in Cambridge, where, Catherine spent some time as well. I know some of you have come back and forth. Kendall is seen as this place where you just kind of bump up if you're in the biotech space. Tell me, what are you seeing, Rafal? I'd like to go back to that question. Do you think there's sort of an ethical component coming out of some of these creative labs? And where are the other hotspots in Canada? Because if I'm right, Alex, you're in Vancouver, is that right? So, and I gotta think Waterloo's all over this. So maybe
yeah, so I mean, on the ethics side, I mean, there definitely is. I think running any company and definitely doing any sort of deeper tech research, you always have that on your mind. But I think it's both D-Wave and Xanadu, though they focus on applications, the core focus is on the underlying enabling quantum technology, and that's a little bit different. It's kind of like thinking back, when the transistors were being built in the first transistor-based processors, thinking about all the potential ethical implications of them, it would stifle innovation. Where I think the bigger risk there is that, governments will not be able to keep up from a regulatory side. Governments, I don't see there being much ethical concern around a quantum computer coming out that breaks encryption, but I do see a lot of concern that'll take, after that happens, 5 years for a government to say, okay, you need a better encryption scheme as the standard for all banking. So I think the regulatory,
like George Church, I keep using because he sort of became this sort of ethicist around CRISPR as well as the inventor. Who this group of us, I think I might be the oldest one on the panel, so I'm not that old. So who has sort of overseen this, and is Canada playing a leading role in that?
I think they are, and I think it's about education. It's not only education about potential customers, but also of policymakers. I'd say we're lucky in Canada that our government officials seem to be very interested on this on a very fundamental basis. So
they've invested a lot of money. You guys have had more investment in quantum in Canada than most countries.
I mean, and late, like definitely places like Australia and Singapore were doing it a lot earlier. But I think now as the technology is starting to roll out, there's a real interest of what needs to happen. And this breaking of public key encryption is used as a stick pretty often in order to drive those conversations. But I think there's much more interesting kind of positive benefits that would be better to drive those conversations. And we're trying to shift away from that, at least when we talk to people. About the hotspots. Oh, sorry.
Yeah, what would you, sorry, go ahead. The hotspots.
I was just going to say about the hotspots. Yeah, Toronto is actually becoming great now, thanks to the CDL. When we went through the CDL, there was no quantum stream. We actually were in the AI, artificial intelligence stream. And since then, there's been now a couple cohorts of actual companies focused on quantum computing. And it's great. They remain in Canada. A lot of them come up internationally. So there's a critical mass starting to build. Traditionally, it has been Waterloo and the West Coast, mainly because of D-Wave there and the Institute for Quantum Computing out of the University of Waterloo. But now we're starting to see that shift, and slowly we're starting to see the AI kind of hotspot of Montreal transition into some quantum research as well. So it's a little bit more distributed than maybe in the US, where it is focused in the Valley. But I'd say it doesn't really make a difference where you are now all that much.
Although I saw that D-Wave's customers include, let me see if I get this right, Google, NASA, and then Oakwood, is it in Tennessee?
Oak Ridge.
Oak Ridge Lab.
Tennessee.
Yeah. So do you guys want to talk about how you're working together with Boston and America? I know Google's putting a ton of money behind this. Can you tell us about who some of the funders are and how Canada and the US are working together?
Yeah, I mean, so Canada is one of our biggest funders and has been for a long time. I mean, they supported us from the very beginning with a lot of innovation grants, and the sort of BDC and PSP have continued to support D-Wave as time goes on. But in terms of the dollars in the industry, it's hard to compete with large U.S. government labs. So Los Alamos National Labs and Oak Ridge National Labs and NASA are all huge, they just have a lot of money to throw at fundamental research. And especially earlier in D-Wave's history and sort of earlier in even a couple of years ago, I say it as if it was a long time ago, a couple of years ago, when this was when this was completely a research question, you really had to find partners who were, who had the pockets and had the long-term view to be able to take on these sort of fundamental research questions. But what's happened in the last couple of years with IBM and D-Wave and Xanadu and Rigetti and Honeywell soon, I think, putting up these cloud-based platforms, is that you're starting to see that shift away from these large government sort of theoretical labs towards the more CDL startup, small scrappy business interested in building something. And I think that that's starting to pull maybe not the funding, but the revenue towards these sort of more commercial, less government lab sources.
So that's always a very interesting moment for an industry. Tell me, if you're a CIO, a CTO, head of R&D, frustrated with something with your computer pipeline today, where should you be looking at quantum, and how does it integrate in with your current pipeline? You want to?
I can take that, which is that, I mean, so I think that naively, like basically, just to be completely honest, if you have a problem in your stack right now, there's a pretty good chance that quantum is not the solution today. I will say that you have a much better chance with hybrid. I know that all of the various vendors in the space are investing very heavily in hybrid computing. So this is this idea of combining classical and quantum computing together. And with sort of hybrid, you can get the best of both worlds, where you can have one, say, unified interface that will route problems appropriatly towards a CPU or a GPU or a quantum computer, or most likely all three. I mean, I really liked the point that Rafal made earlier about, he envisions having a quantum computer as a co-processor in every system. I do think that probably is the direction that this is going. So I guess my advice to the potential CTO is, when you're looking at whether quantum can affect your area, you have to go to your team and ask, like, okay, what's the fundamental bottleneck? And if the answer is like, well, we need bigger pipes, then probably quantum computing isn't going to help with that. You need to go to you need to go to Amazon or something like that to get more data bandwidth. But if they're saying like, oh, we have this really thorny problem with lots of trade-offs and a really difficult set of constrained optimization problems, then that's the kind of thing that quantum computing is I'm starting to perk my ears as an applications developer. I'm starting to say like, oh, okay, maybe that sounds like something we can do. Maybe not quantumly, but that's something. And then when you go down from there, then it becomes a question of, the size of the problem, how difficult it is, those sorts of things. Like what's the exact algorithm you're using, but that's a conversation that takes time.
And
And
I'm just,
go ahead, yeah. Go
I
ahead.
just wanted to add that, to date, and Alex might have a different viewpoint on this, but to date, no one has demonstrated on a real world problem what we call quantum advantage, which is very clearly showing that a quantum computer can do something better than a classical. I think a lot of us in the industry believe that we're right on the cusp of that happening. So maybe in the next 2 to 5 years. But as a result, if you're a CIO, your bottom line definitely is not going to like that. If you're the CTO at an organization that has a research cycle 2+ years out, so these tend to be things like pharmaceutical companies and big oil and energy companies, they're used to taking on that type of risk for that type of research. So that's where, I think quantum really has an impact. It's where you're trying to build in that knowledge base and figure out how you can leverage near-term quantum computing. Because I think over the next 2 to 5 years, there will be real winners and losers. And they'll mainly be based on who has the internal talent in order to actually take advantage of quantum computing.
So is this a talent call we're doing? We're saying like, get yourself smart. If you're young and you have a brain for science, go get smart in, or math, as Alex has proven, go get smart in quantum, because the number of qubits on a processing chip, tell me if I get this right, will increase eventually. The gate error still exists. You have a problem with quantum with noise, right? Noise and temperature are both problems, because then all of a sudden that superposition doesn't know if it's 0 or 1. Am I getting that right? Not really. Okay, Alex, tell me, like, what there, I know that there are problems with us getting to the quantum advantage. And is it that you want a talent call? You want more people thinking about this and researching this with you?
Yeah, personally, I think we absolutely need more people in the space, and we need different types of experts in the space. Like, I think that, we're moving from an era where we're working on the sort of fundamental like hardware, and we're moving really into an area where we can start thinking about these as full stack systems where, you're integrating a piece of hardware into the cloud, and then that, once it's in the cloud, you have to figure out how to hook that up to an existing pipeline. And so I really think that we're, for the first time, reaching an era where you don't necessarily need a quantum computing background to participate in this field and to start becoming quantum aware. The people who build the process, sorry?
Quantum aware, I like that.
Yeah, and I think that, sort of as Rafal was mentioning, it will come, and some of these systems are going to start pushing the bounds of we're going to get a quantum advantage result very soon. We're going to have these systems really starting to impact industry more and more. And the point is that you need to be aware of that. So these things like quantum resistant cryptography, all these different areas are places that you don't need to be a quantum expert to start implementing them and understanding them and using them in your system. And you don't need to be an expert to start using some of these mature cloud platforms as part of your workflow. And by doing so, you can get state-of-the-art results that and also have the sort of peace of mind that as quantum computing continues to improve, you're not going to be left behind. And you see, these days with some of the big players like AWS starting to come into the field, not as necessary hardware providers, but as vendors, because they also don't want to miss the boat on that. They want to make sure that they're sort of quantum secure and that they have all of the infrastructure in place so that as quantum continues to improve and accelerate, that they can jump onto that train.
So Catherine, we have Rafal at Xanadu, we have Alex at D-Wave. Who else should we be looking at between the Boston Canadian corridor where a lot of this is taking place?
So can you say it again, like rephrase that so I answer correctly?
So we know we have Rafal at Xanadu. We know we have Alex at D-Wave. They're way out front on this. Who else along the Boston Canada corridor that you cover should we be looking to or watching?
Yeah, absolutely. So both Rafal and Alex mentioned the hotspot in BC and Waterloo, Toronto. I think another hotspot that was not mentioned is the Institut Quantique in Sherbrooke at the University of Sherbrooke. This is one of the three institute that got major funding from the government in like 5-6 years ago. So one is in BC, one is in Waterloo, and the other one is the Institut Quantique in Sherbrooke. And they are doing amazing things, research there in quantum information and quantum material and quantum engineering. They're also very involved in developing technologies. And I learned that it will be announced next week that IBM Quantum Network is going to install a new hub there with a major player. Yeah.
Wonderful.
So this is really a hotspot. And there is a strong collaboration, for instance, with Professor Alexandre Blais, who's one of the co-inventor of technology that is currently used at D-Wave. So Alexandre Blais is collaborating with Professor William Oliver at MIT. So this is a long-term collaboration. So this is one of example of research collaboration, but both at MIT and Institut Quantique that are developing not only a basic research and generating knowledge, but also pushing that knowledge into innovation and technology and preparing the next experts to work in quantum. I think there are many examples that I can go like a different type of example. I was thinking of Zapata Computing as a startup in Boston that's been spun off of Harvard, and the CSO, so the Chief Science Officer, is a professor now in Toronto, and he's also part of the IQC and the CDL. So there is this, and Zapata has an office also in Toronto. So there is this.
Can you spell the name of that company?
Zapata, Zapata.
And then
yeah, so they are developing algorithms. They are on the software. So, quantum computing is doing, taking two parallel paths, right, so that we can push the development along, and there's the hardware and the software. So Zapata is looking at the software part. And I was thinking also that we have major funding from CFAR program, so the Canadian Institute for Advanced Research, and there are two programs, one in quantum information and one in quantum material. And this is Canadian, and they are very leaders in science there, but also from Canada. But there are also researchers all around the world, including at Harvard. So they're like, this investment of money that Canada is putting for basic research and also technology is in collaboration with strong leaders in the field, including Harvard, MIT, and other universities. But the ecosystem in Boston is very important enough that last year in September there was a quantum tech conference. Right. That was the first quantum technology conference of the sort, and it was in Boston. It was, but I think there was supposed to be a new one in April in the UK that was canceled because of the current situation with the pandemic, right? But the very first conference was in Boston, so because also the ecosystem in Boston and on the East Coast is very it's flourishing.
But sadly, you guys, we only have about 6 minutes left, and I have some questions coming from the floor, so I'm going to put them out there. I want to remind people, too, that there's a Slack channel. I have a lot of notes in front of me from this great panel, and if we have time, I might run through a few of the things that Quantum Advantage can do that Catherine sent me, everything from health to finance to defense, security, energy, and big data. There's so much to cover, but a couple questions. What are the remaining physical limitations of the technology, and how does the hardware need to change or advance to help the field grow?
Sure. The thing is,
because we have a lot of questions.
It depends on which stack you talk about. Each stack has its advantages and disadvantages. So, you know, trapped ions versus superconducting qubit versus photonics, neutral atoms. You know, we at Xanadu believe that photonics is the right approach because of the ease of scalability and the fact that we can do our computation at room temperature. So some of these noise issues aren't as big of a deal. But of course, we have our own different limitations that are just as challenging to get over. So I'd say superconducting qubits are probably falling out of favor with the new up and coming companies. And I'd say if you take a look at most recent investment, photonics is definitely kind of becoming as the hottest, latest thing for companies to focus on. But there's still a good amount of work to do. And it's mainly focused on basically learning how to better control quantum systems. It's kind of the ubiquitous thing across all of them.
Sorry.
Yeah.
I have a bunch, so I'm going to throw them all out there, and maybe you can keep answering as you go with whatever seems of interest. Quantum communications was briefly mentioned. Can you discuss uses and current infrastructure developments? That goes back to my question to you guys yesterday, where I read that the Chinese have some hybrid that they're doing in communications with quantum. Maybe you could give us educate us a little bit about quantum communications.
Sure, I'll jump back in. So I'll wrap up. I think there's a QKD question in there as well. So I'll kind of cover both of these. So there's big initiatives all around the world for quantum communication. The US with the DOE recently just had a big blueprint meeting about developing the quantum internet in the US. The technology is still a little bit ways out for true long distance quantum communication. But it's something that we really need in order to enable the true adoption of quantum computing and quantum sensing, especially. So there's still technological gaps to get over. Again, photonics is probably the only way to do that type of communication. It's what we're used to with the current telecom industry. QKD has been around for decades. There has been some recent advances, and the big thing is that we're starting to see QKD networks be experimented with by large telecom companies. So
and QKD was developed in Canada, right?
There we go.
And Rafal, I think you taught me that the Pentagon and the White House have had a QKD line since the 90s. Is that right?
For quite some time, and then recently, South Korea Telecom with a German telco have started releasing a QKD network in Germany. We've seen, China put large efforts into it. We even know of banks in Canada that have QKD lines between buildings. So it's, or at least attempted to set those up. So it's definitely.
What's the advantage of a QKD line?
So quantum key distribution essentially allows you to have a encryption scheme that is rooted in, I would say, physical security. So it can't be broken by, any sort of attack that is known. So if you need ultra secure communications, you can exchange the keys for that communications in such a way that if anyone were to eavesdrop, it would destroy the key. So you don't have to worry about the fact that somebody might have listened and gotten that information. So it's the highest, I would say, form of security right now that we know for electronic message kind of
based on quantum.
Based on quantum, correct.
Is it a place that we should be worried about? Or are you like, no, we've got all these other quantum things to think about that are going to give us exponential growth in many, many industries?
Luckily, a lot of the things that are being developed for one are applicable to the other. So if you build, like, for example, the Xanadu tech stack, the chips we're building for quantum computing can be used for quantum key distribution, can be used for quantum communication. It actually doesn't take much of a change because it's all about building these systems that are entangled in superposition and being able to control them at a very fine level. So if you can do that, you can definitely achieve quantum computing, and you can achieve the other ones as well.
You guys want to make a bet on who you think the chip maker is going to be from the Qualcomm and Intel days of the past? Who's going to be the quantum chip maker?
Obviously D-Wave.
I think that's a global effort. Everybody is going to win together.
I I agree with Catherine. There will be no losers. I think anyone here would be thrilled to see any other person win.
Yeah, I do agree.
Yeah,
Jokes
stick with it,
aside.
Alex. Go with it. Go with it. I have to say, you guys, I learned so much from all of you, and I want to get smarter on it because, as I say, I have this list from Catherine that says health. We're going to improve brain scans, improved MRI 40 times faster, 25 the cost, drug discovery with material science, finance, increased computational power, precise clocks for high-speed trading. Cryptography, using Shor's algorithm, gravity sensors, design batteries, sifting through big data. I mean, it's really mind-blowing. Do you have maybe each of you could just give us a final word on sort of, you know, what's exciting to you about this, and why do you think, you know, what do you want us to be thinking about? What do you want the conversation to be about? Why don't you start, Catherine?
Well, to me, it's a global collaboration between all the bright minds and all the countries from different disciplines. It's not only physics now, it's not only quantum physics, it's engineering, it's material science, electrical engineering, all disciplines together from different countries to work together, and we'll see which is the first application that shows the quantum advantage. Fine, but I think the most important is that we're all working together, and there's a great opportunity there.
Alex, I'll bring you on. And also, Andrew, come back and join us. Trade Commissioner for Canada is going to join us to close. Alex, what do you have to say?
I mean, I think the most interesting part of the field right now is that it is this sort of confluence of the technology being in the right place and the sort of infrastructure for software being in the right place. And so it's just so easy. It's both a wide open field, but also incredibly fertile. It's so easy to sort of stumble across ideas or new things, or be the first person to apply quantum computing to a whole industry. I mean, that's something that there's almost no other time in history that you can say that kind of thing. And so really that's the part that gets me excited and keeps me excited about quantum computing every day.
Rafal?
I mean, I definitely agree with Catherine and Alex on both their points. I would just add, I'm really excited by the seismic shift that's going to come to computing as a result of the quantum technology that's being developed now. You know, I like to joke that it's probably about 5 plus or minus 20 years out, because we don't know quite when it's going to land. But you know, it's exciting. It's also a little bit scary, because we do have to do a really good job making sure that people are able to take advantage of it, and that all the regulatory aspects around how it will impact the world will actually be there.
Please, governments, listen to these guys. Andrew, I'm going to toss it over to you. Thanks, you guys. Thanks for being patient with my very, very limited knowledge. I really loved learning about it, and I think you guys are all super cool.
Thanks, Heidi. Yeah, no, I think that being able to see a technology that aligns competition and collaboration so well is what is really exciting to see what's going to come from quantum. So, Heidi, thanks again. Fantastic discussion today. I sincerely hope that everybody found today's program informative and maybe educational. And you've begun to formulate some new questions about quantum and maybe Canada too. I encourage you to join in on the conversation on our Slack channel, which is quantumcanada.slack.com. I know there are a number of questions that we didn't get to, so we'll bring those over to the Slack channel and see if we can get the conversation started there. And again, thanks to our host Heidi Legg, our panel, Alex, Catherine, Rafal, and to MIT's Enterprise Forum in Cambridge. Enjoy the rest of your day.